Okay, so what we're going to look at here is something called electrochemical cells. And I'm going to show you how you link this idea to what you've been doing with your experiments where you're observing a change happening or not happening and using electrode potentials to justify that. So to start with, what I've got here is a piece of zinc and some copper sulfate solution. And if I put the zinc in there for a small amount of time, here's where I hope this will happen fast enough for the video. It's starting to. If I leave it in there, then what I notice is that there's a bit of a colour change to the zinc. This copper sulfate is so concentrated that I won't see its colour change. But if I had enough zinc there, or if this was dilute enough, its colour would start to fade as well. Alright, let's see if it's been long enough. Not quite. I'm just going to give it a quick sand, just because there might be an oxide layer there that's stopping this happening. Drop that in there. There we go, good. Okay, so where I have sanded it off, it's starting to go a little bit of a pinkish colour, okay, which is copper forming on there, showing us that it's a spontaneous reaction. So what we've got is the copper ions turning into copper metal, and so you'd infer that the zinc metal is starting to oxidise to become zinc ions. If we looked at the electrode potentials for those two, we would find that it has a positive E0 value, so electrode potential for the cell, as it were, so for the reaction. So that's why it's spontaneous. It happens without being plugged in. You'll notice I have no power source here, okay? And yet, if I hold this up, I've got about 0.9 volts being shown on the voltmeter. I've set this up as a voltmeter. Alright, so there's no power source here. That means that a chemical reaction is creating a voltage, so an amount of energy per coulomb. It's actually, that's what that E0 value that we've been working with actually means. It's measured in volts or joules per coulomb. Because zinc oxidizing and copper reducing has a positive E0 value, is spontaneous, then we can actually use this idea to create a thing called an electrochemical cell. And, sorry, just some people didn't believe me there, just to show that is actually quite pink. Okay. And that's what this is. This is an electrochemical cell. Over here I've got a zinc solution with a zinc electrode, just a piece of zinc with a wire connected to it, a zinc electrode in it. Here I've got a copper solution with a copper electrode, piece of copper bound to a wire, that's what it means, with a copper electrode in it. You'll notice I've got a bit of paper connecting the two of them. This thing here is called a salt bridge. I've made it with some filter paper that I've soaked in potassium nitrate. And the reason that that's there is it basically completes the circuit for the physicists out there. What it does is it allows for the nitrate ions to go one way, the potassium ions to go the other way, to help keep the charges balanced in each of these things here that are called half cells. 2 half cells makes a cell. This is only a voltmeter, so it's not actually using any of that energy. It's only measuring the energy difference between the two. Alright? So, if I put zinc in a zinc solution, there'll be no observable reaction, will there? I won't see anything happen. Because zinc metal in a zinc solution, there's nothing to drive that reaction. Same with copper in a copper solution. But if I connect them with a salt bridge and then plug it into an appliance or a meter, so something to use up a little bit of energy or to measure an energy difference, we end up getting a chemical reaction occurring. And eventually we'll see that and you can probably see it quite clearly there, the bit of zinc gets very, very thin at the bottom. So we know that it's being eaten away or corroded. So this must be the oxidation reaction, just like the zinc being oxidized in here. And over here, we'd expect the copper to get fatter and fatter, and that's probably a bit harder to see, but it looks a lot cleaner, doesn't it, than it does up the top. So that would suggest that there's a layer of copper, pure copper, being formed on the outside of that. And that's exactly what's happening there. So reduction, these copper ions are turning into copper metal. Then in the salt bridge, the potassium ions are being forced into there to replace those copper ions, to keep it neutrally charged. And the nitrate ions are flooding into there to make zinc nitrate over here. Okay, because you need to balance out the zinc 2+ ions as well. So it's that movement of charged particles is what we call as part of what's required for an electric current. Then we plug it into the wires and we see that there would be a flow of charge in here. So if I set this up differently as an ammeter and put an appliance in there, you'd see a small current going through it. Without an appliance, the battery doesn't drain. Okay? The voltmeter is not an appliance. It's measuring the voltage only. Okay? So it's set up in parallel. To put it very simply though, if we did have a lamp in there, if this is oxidation, it's called the anode. And if this is reduction, it's called the cathode, and this is the bridge. So it's A, B, C. I'll show you later how to write that up shorthand. The anode is where oxidation is occurring. So that means that it's losing electrons. Those electrons are going into the wire. So which terminal of a battery would that be? Negative. It's going to be the negative. It's going to be giving off electrons. This one's going to absorb electrons, so attracts the electrons. So which terminal of a battery or a cell would that be? Positive. Okay, and so the cathode is positive and the anode is negative. This is the opposite to electrolysis, which you learned about briefly, probably last year in the redox topic. Would have been only very briefly. All right, so just to recap, I can show a spontaneous reaction just by doing it here. I can prove that it should be spontaneous by using electrode potentials. I can use that idea of a spontaneous reaction to create a cell from two half cells, then create a voltage that I could use to power an appliance. And that's the practical use of the redox stuff that we're learning now. This is also how we found out those electrode potentials, by the way. We put the hydrogen half cell on the left-hand side, so is the anode, and every other cell is measured against it and either gives a positive or a negative value. If it's negative, it means the electrons are flowing the opposite way to what we'd expect. So it means that actually when hydrogen's being oxidized, yep, there's reduction occurring there, but if the voltage is negative, if the electrode potential is negative, when it's connected to hydrogen here, that would actually be reduction and this would be oxidation. Okay. So that says that if you have negative electrode potential for a cell or a reaction, it means the opposite would have happened. That's all that means, the opposite to what you expect. And that's how we use those values. Any questions on the link between this and this? That's probably the main thing. And therefore, the relevance of those numbers we were working on yesterday. Cool. All right, we'll stop there then.